Good morning. Today we're going to talk about the electrocardiogram, where we're going to use a PowerPoint presentation. I think I've got this set up so I can toggle back and forth between my laptop and the main room computer so that we can record it while we're doing the PowerPoint, but there's a slim chance that there won't be a video when we get done. So I'm hopeful that there will be. Okay, but before we begin, just let me note, on Friday we're going to continue on Chapter 7. We're going to be talking about defibrillators and pacemakers. And it will probably also be a PowerPoint presentation. And you have homework that's not due today, but due a week from today in Chapter 7. And we'll talk about a few more of those problems today, but you want to hopefully try to get a start on it this weekend so that you won't have to wait for the last second. So let's see how this works. That, and the electrocardiogram. Electrocardiogram is usually called the ECG, although the German word for electrocardiogram actually had a K, so sometimes you'll hear it called the EKG. Exactly the same thing. It's just whether you like German versus English initials. So, this is the person who first recorded the electrocardiogram, William Einthoven, and he got the Nobel Prize for this work. He's really the example of someone who started in medicine and then made the transition later in his career more towards physics and engineering. So it's fairly common for people like me who start in physics to then make a transition more to biology, but it's rather rare to do it the opposite direction. So we'll be talking about some of Einthoven's work and how it's led to the electrocardiogram for today. So this is what's known as Einthoven's triangle. So usually the simplest electrocardiogram, you have a lead on one arm, a lead on the other arm, and a lead on one of the legs. And you're recording potential differences between the two. And which two electrodes you're reading is called the lead. For instance, lead 1 is measuring the potential difference between the left hand and the right hand. Lead 2 is between the left hand and the leg, and so on. So there's 3 main leads, and then you can put linear combinations of them together to get these auxiliary leads. It's a simplified way of examining the electrocardiogram. We're not going to spend a lot of time worrying about what leads, but the electrocardiogram can look a little bit different depending on which leads you're looking at. And if you go into a doctor's office nowadays, they'll put more than just 3 leads. They'll have leads all over your chest to get even more information. So here, I believe this is Einthoven with his original electrocardiogram machine. They didn't have oscilloscopes or other ways to measure voltage easily. He had what's known as a string galvanometer, where small currents would go through a string in a magnetic field and they'd deflect, and you'd watch that deflection or record it on a piece of paper. He didn't have good electrodes to attach to his skin like we have nowadays. So what he did is he put his feet and his hands into basically a big solution of dilute sulfuric acid. He wanted to have something that would make a good electrical contact with the body and make sure it'd be a clean, sort of fresh surface. So it wasn't strong enough to dissolve his hand and leg, but it was strong enough to make good electrical contact. So that's really the way Einthoven originally measured his Einthoven's triangle. And basically, the whole arm is pretty isopotential. You don't have currents going back up and down the arm. So if you measure here, it's essentially the same as measuring there. If you measure there, it's essentially the same as there. And you measure down the foot, it's basically like at the base. So there's Einthoven measuring the first electrocardiogram. We've come a long way since then. Okay, let's start talking about the electrocardiogram because that's our main topic for today. And we're going to use some of the ideas we had from last class, because you see pictures of the heart here. So you start the electrocardiogram, there's basically 3 waves. The P, then the QRS complex, and the T. The P wave comes from the atrium contracting. So what happens is, remember, you have the SA node, where it's a natural pacemaker, where the signal starts. And the SA node, the signal then propagates through the atria, both of them, and it goes more left to right, And you can represent that as an approximation as a dipole. We talked about representing electrical potentials as dipoles. Essentially, you can describe that as a dipole pointing more or less, I guess this would be right to left in this case. And that dipole gives an electrical signal, and that's what creates the P wave. So P wave is atrial depolarization. Then the signal goes to the AV node, and the AV node tissue, although it's conducting a signal, there's not much tissue there. It's a very small amount of tissue and it's propagating along, so it doesn't, its dipole is really small. Basically, you don't get any signal while you're going through the AV node and the bundle of His until you really reach the ventricular muscle. So once you finally reach the ventricular muscle, remember you go through those Purkinje fibers, they spread the wavefront, so it basically starts over the entire inner surface, or the endocardial surface, and then it propagates across the heart wall. So this propagation across the heart wall creates a dipole that you can think of it as a whole bunch of dipoles, but they add up to more or less in the downward direction. And that gives you this QRS complex, which is by far the biggest signal in the electrocardiogram. And we'll see a little bit more why it's separated into three pieces. But sometimes you see a Q wave, sometimes you don't. But you always see the QRS complex if the ventricles activate. Then the entire heart becomes in the plateau phase of the action potential. So it's essentially up in the plateau. It's uniform, because remember the plateau is very long. And the question then is, it doesn't produce any dipole, because if you're all the tissues, all the same potential, there's no potential gradients, you get no dipole. So there's a quiet time between the QRS until the next. And then the wavefront, the parts of the heart begin to repolarize. They don't all repolarize at the same time. More or less, the outside repolarizes first, and the inside repolarizes last. So you end up getting a dipole associated with ventricular repolarization, and that's the T wave. Now you might ask, well, why didn't you get something that was involved with atrial repolarization? Well, literally you do, but it's usually really small. Notice the T wave is a lot smaller than the QRS. So the repolarization of the atrium would be a lot smaller than P, and it's kind of buried in the QRS, so you never see it. So basically, you don't see a signal associated with atrial repolarization. You just get these three ideas. And that's the heart of the normal electrocardiogram. And one of the things we're going to be doing is looking at deviations in the signal from this normal and trying to use that to diagnose diseases. So, homework problem 7.24. That's one of your homework problems in your homework assignment. I want to know what's roughly the duration of this QRS complex. Well, to do it really accurately would be a lot of work. But more or less, the Purkinje fibers come down and spread the signal over the entire endocardial surface, and then it propagates through the heart wall. And so if you approximate the heart wall as being more or less uniform thickness, then if you know the propagation speed, you can figure out how long there's a dipole in the heart wall until it reaches the outer surface, and then the whole thing's in plateau. The thickness of the heart wall is sort of a centimeter, maybe in thickness. That might be a little bit overestimate, but it's not bad. And the speed depends on the direction of the wavefronts. It depends on whether you're going along the wavefronts or across. But when you're going, most of the fibers, along the fibers or across, most of the fibers are kind of in this direction. They're not propagating straight across the heart wall. So you're propagating across the fibers. So your speed's pretty slow. It's like 0.2 meters per second. You could say 0.2 millimeters per millisecond. So 0.2 meters per second, that's sort of like, let's see, I'm going about a meter, so I have to go slower than this. Something like that is the speed of the wavefront as it crosses the heart wall. So you take the speed and the distance, and you don't have to do much more. You can calculate the time it takes to cross the heart wall. And that's more or less the duration of the QRS complex. So that's one of the problems in your homework. That one, if you find yourself doing a lot of work, you're doing it a lot more, making it more difficult than what I mean it to be. Okay. Now, there's something funny about that last picture that I showed. Why does the ventricular endocardium repolarize first? So let me say what this means. You start with the wavefront here on the endocardial side, and then it propagates across. Now, if every action potential was the same duration, where would you expect it to begin to recover first? It would begin to recover first where it began to propagate first. It would recover first on the inner surface, and then slowly recover out here. But that's not what I'm showing. I'm showing it recovering on the outside first, and then eventually recovering on the inside. And that changes the direction of the dipole. So it makes a big difference. So we have a problem that's known as the inversion of the T wave. So problem 7.26 in your homework talks about the inverted T wave. It kind of steps you through it. But the idea is if you can make the action potential shorter on the epicardium, the outside, and longer on the endocardium, you can make this work. So it's a real long action potential on the inside. Okay, it starts here, and then it slowly recovers, and since it's so long, it recovers finally on the endocardium. The epicardium was much shorter. So basically the problem asks you to draw some pictures and to make this argument, essentially the argument I just made about how you can end up getting an inverted T wave. So it stresses the fact that the action potential duration is not the same in all parts of the heart. It varies throughout the heart. In particular, the T wave not being inverted compared to the QRS is evidence that it's got to change between the two surfaces. So the problem will walk you through it, but I want you to, it's basically a qualitative description of how that works. Okay. Here's a little more detail. And I show this in part because above shows what's happening in the heart. Red is tissue that's depolarized or in the plateau phase. Blue is tissue still at rest. And you can see that this is during atrial depolarization. So that's part of the P wave. You have a wavefront that's propagating pretty much to your left, or to my left, but also propagating down from the SA node down towards the AB node. And you see that this dipole, you can put it into this triangle. This was Einthoven's triangle for the leads. And this can help you tell which lead shows what polarity. For instance, lead 1 has a projection of this dipole on the lead 1. So it's basically expects to have a positive polarity because you're measuring, I believe you're measuring this with respect to this. And the dipole more or less points in that direction, so you get a positive signal. All these signals are positive in this case, but you see this dipole is almost perpendicular to lead 3, which means the signal is real small, which means you get a lot smaller P wave in this lead than you get in this lead. So you can kind of see qualitatively why you're getting different signals in the different leads. So it goes through, gets the entire atria now, fire, and then you get it crossing the atrioventricular node, no signal, and then it reaches the inside of the surface of the heart. And I said that it starts more or less over the entire inner surface, but actually it starts just a little bit earlier on the septal wall of the left ventricle. You're going to see, if you look at these times, this is 2:20, and we're going to look next. The next slide is going to be a very much shorter time. So it doesn't last too long, but initially you get a dipole that's pointing over here to your right, and you see then you get a very small signal for, and this would be the Q of the QRS complex. Very small signal in this lead, but you get quite big signals in this lead, and this leads up, and that leads down. So it really depends on which lead is for the polarity of the signal. Okay, that was at 2:20. Now, here's 2:30, 10 milliseconds later, and now you see the Purkinje fibers, which spread the wavefront very quickly, have spread it over almost the entire endocardial surface of both ventricles. So now they're both firing, and it's beginning to cross the heart wall, and you get a big signal that's down and to your left. So you get a big signal here, which now gives you a large positive R wave a large positive R wave here and kind of a smallish positive R wave here. So what's that saying is the R wave is really the biggest wave, and it's when the main signal's crossing over across the heart wall. And it finishes up. Let's see. This is the left ventricle over here. The left ventricle wall is a little thicker than the right ventricle because the left ventricle's got to pump blood more powerfully to the entire body. The left and right ventricle just over the lungs. So it's a little thicker. So once it completely becomes in the plateau phase in the thin right ventricle wall, they're still crossing the left ventricle wall. So the dipole swings up a little more to your right, and this would be the S part of the wave as it that's at 240. So this all happens fairly quickly. In a short amount of time, you get this large QRS complex. And here it's just at the tail end of that, just crossing and finishing up, going across the heart wall. And actually, no, this is ventricular repolarization. It's crossed the heart wall, everything's in the plateau phase. And then, because the action potential on the outer or epicardial surface is shorter, it begins to recover. And the inside hasn't recovered because it's a longer action potential. So you get the wave front actually crossing from out to end, but the dipole points along the potential gradient from depolarized to resting tissue. So it's pointing out like that. This is your T wave. So the T wave polarity, see, can depend actually on exactly which way this dipole is pointing. And finally that gets over, and you're back to rest, and the whole thing's over, and you have your electrocardiogram. And again, the electrocardiogram, how exactly it looks depends on which lead you're looking at. Lead 1, 2, or 3. So that's a little more detail of what a normal electrocardiogram looks like. So if you go into the hospital and you see this kind of signal, but remember it's repeating, it's like once every second or maybe 1.5 times a second. So you're seeing this, and usually they have a little EKG meter, have a little beep that'll trigger on the R wave. So you're sitting there, you watch this thing, going beep, 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 and this thing's doing, and it looks more or less like this. Be happy. Things are looking normal. We're going to see there can be lots of abnormalities. Okay, now a little bit more quantitative. It used to be that electrocardiograms were always plotted on this kind of graph paper, and it was a standard graph paper all electrocardiograms come out on. And it's not real obvious in this case, but there are small boxes like this, and 5 small boxes on each side make up big boxes, and usually they're more of a bold face line, and it's not so obvious on this. But you can see it a little bit. For instance, what I call a big box is this thing here. Let me add. This thing has a U wave. Sometimes you can get strange waves. You can ignore U waves for what we're concerned about. It's not anything you need to worry about. But this is if you look at an electrocardiogram, you get one of these big boxes, and what you want to know is it contains your time scale. One of those big boxes is 0.2 seconds. So it's like it's a standard that's always drawn on. So there you have your 0.2 seconds, and in the other direction is the voltage, 0.5 millivolt. QRS complexes are on the order of 0.5 millivolt. We said that extracellular potentials are a lot weaker than intracellular potentials. The intracellular potential changes by about 100 millivolts, from say minus 80 to plus 20 or even higher. Extracellular potentials are a lot smaller, 100 times smaller. All right, so now you have the information you need to figure out the heart rate. Because here we see a QRS complex, and this would be 1 big box, 2 big box, essentially 3 big boxes. That means 0.2 times 3, that's 0.6 seconds between QRS complexes. So it's 0.6 seconds. If you take the reciprocal of 0.6, you get 1.67 hertz, so that's the cycles per second. But nobody ever specifies EKGs in hertz. They always convert 1/seconds or beats per second to beats per minute, multiplying by 60. Multiply 1.67 times 60. This is 100 beats per minute electrocardiogram. 100 beats per minute is just about as fast electrocardiogram you can have and still be in the normal range. This is a normal electrocardiogram, but just barely. If it was much faster than this, you'd consider it an overly rapid electrocardiogram. If you had 5 of these big boxes between the QRS complexes, you'd be going then at 1 hertz, because 5 times 0.2 is 1 second, so that'd be 1 beat per second, or 1 hertz, or 60 beats per minute. 60 beats per minute is about as slow of a electrocardiogram as you can have and be considered in the normal range. So you're usually your heart rate's usually between 60 to 100 beats per minute. This is a resting heart rate, not if you're exercising. And that translates into 3 to 5 of the big boxes if you're just going to try to do it from the way the thing looks like. So that's the way to kind of keep track. If you give an electrocardiogram, you can then figure out the heart rate just by counting boxes, really. Question?
Just to make sure, if you were to give this to us on an exam, would it be the same scale, like 5 boxes this way is 0.2 seconds, 5 boxes this way is half a microvolt or millivolt?
Yes.
Okay.
Yes, and especially if I wanted you to get the rate, I would make doubly sure that it was more clear than it is here, because here it's a little not real clear where the big boxes are. You have to kind of count the little boxes. But on an exam, I would bend over backwards to make sure that that was clear. There is a homework problem where you're going to have to get the electrocardiogram, in fact, the rate. Let me see if that's, okay, that's not this next page. Wait, is that? There, homework problem 725. 725 gives you an electrocardiogram in the book. And I'll just take a look at that now that you got me thinking about it. I wonder how easy that is to interpret the boxes. 725 has you look at electrocardiogram figure 7.30, determine the rate of the atrium and the ventricles. So 7.30 is an electrocardiogram where it's a little bit hard to see the little boxes. Basically, those are all little boxes. The big boxes aren't obvious, but you can count 5 of the little boxes and it'll give you a big box. So yeah, homework assignment, I can't promise you it'll be absolutely easy to read, but on an exam, I would make sure it's easy to read. So that's another one of the homework problems, 725. So we talked about, it's really 3 of the problems on the next assignment. Okay. Now here's one of the things that can happen with electrocardiogram. This one's called ST segment elevation. This is what happens if a person has a heart attack. So suppose you have a heart attack, which means one of your arteries that's feeding blood to the heart gets blocked. And remember, there's lots of arteries feeding blood to the heart, so your entire heart doesn't go ischemic. Ischemic means lacks oxygen. Only some small region of the heart becomes ischemic and basically injured. We're going to represent that as the red region here. And what happens is that the rest of the heart sits at resting potential, but this injured area can't support a resting potential, so it's up high, a higher potential, usually close to 0. So what that means is that there's dipoles. There's dipoles in the resting heart. Usually the resting heart's uniform, there's no dipole. When you have injured heart, you have these things called injury currents, which represent dipole sources. So that when it looks like the heart's at rest, it's actually below 0. It's hard to see that because it depends on whether you're AC coupled with your recording device, but you get below 0, and then you fire an action potential.
Sorry, I dropped that.
All right. Then you fire an action potential, and the whole heart becomes depolarized, including all the healthy tissue, and plus the injured tissue is already depolarized. So now the heart looks more or less uniform. So that is that's during the plateau phase. Actually, it's during the depolarization phase and the plateau phase. It looks like there's no dipole. Okay, so that's what you expect, no dipole during the plateau phase. And then when it goes back to rest, you're back down where there's dipoles present. So the bottom line is you have this, what's called ST elevation. You have a P wave, QRS, but the S doesn't come down to zero. It stays up high until the T wave finishes. And so instead of looking like a normal electrocardiogram, you have this elevated area between the QRS and the T. ST elevation is a sign that you've had some damaged tissue in your heart. So that's a sign that you may have had a heart attack. So one of the first things doctors will do is they'll look for this ST elevation. That's not a good sign, but the heart's still functioning fairly properly. It's just that one region of it probably can't contract properly because it's injured. This is an example of how you use the electrocardiogram to diagnose something. All right. Another homework problem that we want to discuss. We're going to discuss first problem 43, which is very similar to problem 42. But let me first say problem 43. During sinus exit block, the SA node functions normally. SA node is the pacemaker up in the right atrium. But the wavefront fails to propagate from the SA node out into the atrium. Sketch 5 beats of the electrocardiogram with all beats normal except the third, which undergoes sinus exit block. So sinus exit block is something that comes and goes. So here's the first two. And this is just a crude drawing, but you're supposed to be drawing something like this in your homework. You see a P, a QRST. P, QRST. What's going to happen for the next beat? Because basically the SA node's firing right before the P wave here. The SA node fired right before the P wave here. The SA node's going to fire here. What do you see next?
No P wave.
No P wave. And if there's no P wave, there's no way to get across to the ventricles. No QRS. You see nothing for one beat. We're assuming that you just have the exit block on the third beat. So essentially you have flat line until the SA node fires again. So the SA node's working just fine. You can't see it because the SA node's basically silent in the electrocardiogram. But it's not getting out to the P wave. So this is how problem 43, if I ask you to sketch what 5 beats of the electrocardiogram would look like, you'd sketch it like that. In this case, it's not too important. You have the scales and the graph paper all set up right. I just want to see qualitatively what it looks like. Now, problem 42 is part of the homework, so we won't do this completely, but let me just ask you, suppose you change your disease so that now the wavefront gets out of the SA node and propagates into the atrium, but your AV node that connects the atrium to the ventricles is blocked. How is that going to change this signal? It's going to be the third beat that's going to see the block. How's that going to change what the electrocardiogram looks like? Anybody can throw it out if they want, but it's basically on the homework. So, but feel free to pipe up if you want.
What would going to be a P wave and no QRS?
Exactly. If there is a blockage in the AV node, you won't get the P to go across to the QRS, but you will get the P. So the main difference would be right about here. You have a blip P wave, but now you have no QRS and T waves. Yeah.
Would you also see a second, real polarization of the atria now that QRS is not overwhelming you?
Well, that's a very good question, and you might, if you look real carefully, see that. But it's still going to be very small, and there is, unlike these drawings, there is some noise, and whether you'd actually be able to detect it or not, I'm not sure. But it's a good question. And we're going to see another example of AV block, second degree AV block here, and maybe we'll take a look and see if we see it in some of the real electrocardiograms. All right, so that's homework 43. 42 is the one you're going to do. So we've essentially done it. If you remember, if you understood and remembered, you could draw it out right now and be done with that problem. Okay. So those examples that we've just looked at are examples of how you can use the electrocardiogram to diagnose things. But what do you need to know for the exam? Well, there are going to be 12 electrocardiograms that I want you to know for the exam. So you're going to have to be able to identify them. So we're going to go over those 12 and see exactly what those 12 cases are. So let us begin one by one. Okay, first, this is the normal sinus rhythm. This is what we were talking about before. Now, sometimes it's not terribly obvious. Things can look a little funny between different people, but you see a P wave, kind of a smallish P wave, QRS, T. How many big boxes? Here you can see the big boxes nicely. 1, 2, 3, 4, 5. It's about 5. This is about as slow a QRS complex as you can have and still be normal. But I would say this still falls in the normal range. It has about about 60 beats per minute, because 5 boxes would be 1 second. So it's going about 1 hertz, or 60 beats per minute. It's normal. Okay, so that's an easy one. If it looks normal, you're done. You know the normal sinus rhythm. Okay. Now what can happen? This is called a sinus bradycardia. Bradycardia is a fancy word, and it comes, I believe, from the Greek brady for slow. So it's a slow sinus rhythm. So what you have here is a normal-looking electrocardiogram. I see a P, I see QRS, I see T, I see P, QRS, T. The difference is that it's got this long, quiet stage between the T and the next P. So how many big boxes are it? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 6.5 basically big boxes. Well, that's a slow rate. 6.5 times 0.2 is, you got to do the math. It's going to probably be going somewhere around 45 beats per minute or something like that. That's unusually slow. So what does that mean? Well, if this is a normal person, the sinus bradycardia probably means they're not getting enough blood pumped, because their heart's pumping not fast enough. Now, even if each pump was as effective as in a normal person, because it's not beating very fast, this person's probably going to be kind of sluggish, lethargic. It's not going to be too able to function. They're probably not going to be dead. They're probably not going to be fainting. But they're going to have a hard time. Yes?
So, I have heard of people that they don't brag about the resting heart rate, but they talk about how they have like a 40 beats per minute resting heart rate. And they're runners.
Exactly.
They run every single day. I don't know if that changes things.
This could be a perfectly normal, in fact, a super healthy person. If your heart is unusually strong, so that each pump can pump more blood than a normal person, then you can get away with a lower heart rate, and you can still get plenty of blood. So this might be a normal person who's kind of feeling sluggish and lethargic, or it might be a marathon runner who's just lying down, resting between races, and in that case, this would be perfectly fine. There'd be no problem. In fact, they might brag about it, but they have to have a good, strong heart that's able to pump more blood than you expect for each pump. Yeah. So sinus bradycardia is not necessarily an illness. So you go into the doctor, and the doctor is going to want to look at the electrocardiogram, but they're also going to want to talk to you about your history and look at your general physical condition before they make some diagnosis. Yeah.
So typically, if it's less than 60 beats per minute, it could be that, but the doctor has to look at more.
Well, it would definitely be a sinus bradycardia, but whether the sinus bradycardia is something that's unhealthy or healthy depends on the person.
Okay.
But I think you still classify it as a sinus bradycardia in either way. All right, so, and by the way, sinus, because you have a P, QRST, everything looks normal, that means that this is probably coming because the sinus node itself has slowed down. Because once it fires its action potential, everything else looks pretty normal. So it's a problem with the sinus node. Here's the opposite problem. Here you can see P, QRS, T, and then almost immediately P, QRST, P, QRST. Each one looks fairly normal, but there's almost no time between the end of the T wave and the next P wave. So how many boxes? It's like 2.5 boxes. This is running maybe 120 beats per minute or something. It's running really fast. That's a tachycardia. Tachy means fast. So if the sinus, this looks like a sinus node problem because the whole PQRST looks normal, except that it's just crammed together. So it looks like it's the sinus nodes just going way too fast. This problem, is this a problem? Well, this if you're going too fast, the pumping actually begins to be less effective. Each pump can pump less blood, so it can be a problem. This could be a normal person exercising. I'm assuming this is a resting electrocardiogram. This is probably me after getting on a treadmill for 20 seconds. I mean, I'd be in this situation. Okay, so it depends on the situation, but if this is your resting electrocardiogram, you probably have a fast heart rate. Yeah.
With this graph, the baseline moves up and down. Is that just random chance, or does the heart at times become titanic?
I would say that is probably electrode motion or something. It's I think that's artifact. That's why a lot of times you'll have your measuring device AC coupled to kind of get rid of baseline drift, but that's essentially baseline drift, and I don't think that has anything information in it. I think it's an artifact basically. Yeah.
So what's the beats per minute that would, like if you're resting, what's the beats per minute that would be considered that?
Well, let's just say it's 2.5. You have to count up to get it real accurate, but 2.5 boxes, that would be 0.2, 0.4, 0.5. So that would be 2 hertz. So that would be 120 beats per minute. Yeah. So that's the way you figure it out. Probably the best way to do it is to start and count boxes for like 10 and then get the total time and divide by 10 so you can get a more accurate reading, because it's not exactly metronomically steady, but it's pretty steady. Now, how do you treat people with either sinus bradycardia or sinus tachycardia? Well, especially tachycardia, one thing you can do is you can give them drugs. There are certain drugs, and we're not going to go into the whole drug business. There are drugs which will basically slow down the heart, and that would be the first thing you'd do for this person. If you had the bradycardia, there are drugs that will speed up the heart, so that'd probably be the first thing you'd do. And if that didn't work, you could go with a pacemaker, which we'll talk about next class. But probably both of these, I think the first thing the doctor would do is might put you on some drug if they felt it was a serious enough arrhythmia. Okay, so that's 2 arrhythmias plus normal, so we've gotten through 3. Now we're going to talk about the problems with the atrium. Okay, this is atrial flutter, and we're going to talk quite a bit about reentry in the heart. But the idea of reentry is that, remember, the whole heart can you propagate anywhere in the heart. So you can start, here's the atria, so here's the ventricle, and then you got the atria up here. And you can have a wavefront in the atrium. It's not normal, but you can start propagating in this direction, but not in other directions for some reason. Come around and swing around and then come back and start going in a circle. This is called reentry. And the beating of the atrium then would depend not on what the SA node's doing, but how fast you go around this loop, this reentrant loop. So what you see here is the P waves look all screwed up. You can see them, and it's almost unrecognizable as a P wave. But you got P wave, P wave, P wave. They're very fast, like one box. So that means that this loop is going around in like 200 milliseconds, 0.2 of a second. It's going around and around and giving P waves each time as it goes around. You can't drive the AV node that fast, so only occasionally does this get across the AV node. The AV node has a long refractory period. You can't drive it at 0.2 seconds. So occasionally you get a QRS, which isn't real big on this picture, but it comes through. It usually is after 3, but occasionally it'll be after 2. It depends exactly on the situation. You get a fairly normal ventricular beat, but the atrium's all screwed up. Atrial flutter is not real healthy because the atrium's not going to be contracting really properly. Instead of the atrium contracting kind of as a whole, it's going to be constantly kind of pushing blood back and forth. It'll function a little bit, but it won't be real effective at pumping blood into the ventricles. So this person's probably going to have ineffective pumping of blood, even though his ventricular rate's more or less okay. It's probably not going to be too effective at pumping blood. Yeah.
So what would you define like each heartbeat? Would it be after every like QRS?
If you were defining the rate, you would, if I just asked you for the rate, I would probably assume it's the QRS, the biggest signal. I could ask you for the the atrial rate and the ventricular rate, and then you'd have to, the atrial rate would be off these P waves, and the ventricular rate would be off the QRS. So it depends on exactly how it's worded. Okay, so atrial flutter is you got a problem in your atrium. It's not terribly, it's not lethal, but it's probably going to have some symptoms. You're probably going to feel a little sluggish and not pumping a lot of blood. Here's another case, atrial fibrillation. Fibrillation means instead of having one loop that's going around and around, you have, here's your ventricles, your atria, and you have a bunch of these little loops kind of going all over the place. And they're kind of chaotic. It's almost like turbulence. So your baseline looks like noise. But it's just in the atrium because the QRS complex look kind of normal. Occasionally they'll go through. It's hard to predict when they'll go through. But once they go through, the QRS and then T waves look more or less normal, but they're on a noisy background, and that background's from the atrium. So atrial fibrillation is really common these days. In fact, it's one of the big things that the medical device companies are looking at now. My dad had a bout of atrial fibrillation. He ended up in the hospital. It wasn't life-threatening, but he started building up a lot of fluid in his body because his blood wasn't pumping really effectively. It's a problem. One way you can treat this is you can actually go in and if you know where sort of some key places to kill the tissue off, you might be able to kill it off at a few spots and stop atrial fibrillation. It's known as ablation. So oftentimes you'll thread a catheter up into the heart and you'll apply some high radio frequency energy and you'll kill part of the heart. You'll ablate it away. And you won't go all the way through the wall, so you won't have a hole in the heart. You'll kill some of the tissue, and you'll get rid of this fibrillation, so then you can get back to a normal heart rate. Or first thing the doctor would do is they give you some pills that would affect the atrium signals to try to remove it with a signal. Or you can do what my dad had, is you can apply a defibrillator and shock the atrium. You got to be a little careful because as we'll see, if this happens in the ventricle, it's a lot bigger problem. But in the atrium, it's not that big of a problem, so you got to be a little careful when you're shocking because the shock could start in the ventricle. So it's a little bit risky. Atrial fibrillation, a person's going to probably be conscious and able to function, but the person's not going to be, they're going to be out of breath, they're going to be sluggish, they're not going to be out playing tennis or doing some kind of exercise. They're not going to have a good enough delivery of blood. The atria are not filling the ventricles before the ventricles pump, so it's not going to be real effective. Yeah.
So what's the difference in like the EKG for somebody that has that? What's the notable difference?
The main difference is you have essentially noise with some normal QRS complexes.
Oh, so there's no like DMT really?
There's usually a T. I think you could get a T. I should probably also include a T, but there's no P's. The P's are gone and replaced by essentially noise. Where this is atrial fibrillation, atrial flutter, the P's are replaced by sort of a sine wave looking thing with some QRS complex and T waves coming through it. So the main difference between atrial fibrillation and atrial flutter is atrial flutter has more of an organized structure in the atria, whereas atrial fibrillation has a very unorganized signal. So if I asked you to distinguish between atrial fibrillation and atrial flutter, I'd have to give you a pretty clear-cut case. This is pretty clear-cut that it's fibrillation, because it's a very noisy signal on the baseline. Okay. Let's see. Next, first degree AV block. Now we're going to start talking about the problems with the AV node, the connection between the atrium and the ventricle. Now, can anybody tell me what's wrong? I got listed up as this first degree AV block. Well, what looks wrong with this electrocardiogram?
The T wave is
The
really big.
T wave's not so bad. I mean, it's got a funny little dip there, but it's not the T wave that's a big problem.
The,
Anyway, seems out of place.
the
what?
PQ segment seems elongated.
Okay, there you've got it. You said it in the proper way. Some of you might have kind of seen it. Here's the P, and if you look at a normal electrocardiogram, the P is followed by QRS in a fairly short time, usually less than 1 box. Okay, so the P wave, it takes about a tenth of a second, maybe up to 2/10 of a second to cross the SA node on the normal tissue and get into the ventricles. Here, it's taking you a box and a half or more to go from the P to the QRS. What that means? That means that the AV node, it's functioning, but it's kind of slow. This is not a big problem. If you have first degree AV block, you're pretty much normal life's style. However, it says to the doctor, I better watch this person, because first degree block, AV block, can lead over time to a worse problem where you begin to fail to propagate across the AV node, and that's a different type of second or third degree heart block. So if I was a doctor, and remember, I'm not a medical doctor, so I'm trying to give you a general idea how this works. Go to medical school if you want to really learn the detail. Okay, but if I'm a medical doctor and I see this person, I'm not going to give him any pills. I'm not going to give him a pacemaker. I'm going to have him come back every year for electrocardiograms, maybe every 6 months if he's an older person, to make sure that we don't miss this getting worse. All right, so it does get worse, and here's what we have is second degree AV block. This is the one that we talked about in one of those homework problems. You have, let's start here. PQRST, PQRST, PQRST. But notice the P is getting a little longer before the QRS. Longer still. Then T, P, nothing. This is when you drop a beat. Sometimes the P, Q segment gets longer successively until it drops, and sometimes it doesn't. Sometimes it's pretty steady until it drops. But if you're dropping occasional beats like this, you still see a P wave, but you don't see a QRS and T wave. That's second degree AV block. How important is this? How big of a problem is this? For this person, it's not a huge problem because you're dropping every fourth or fifth beat. Okay, that reduces your effectiveness of pumping a little bit, but maybe by 20% or something. Not a huge problem. If you start dropping every other beat because of this, then the second degree AV block becomes a bigger issue. So how big the issue is depends on how many beats you drop. But you can tell it because you still see the P wave even though you don't see the QRS and T. So that's second degree. And guess what? There's a third degree AV block. This is when you have P waves. Here we can see P like a metronome. P. It's hard to tell, but that's a P. P. There's a P buried in the QRS. P. They're going like clockwork. And the QRS are going like clockwork, but at a much slower rate. What happens is the AV node completely fails. So you have your P waves going like clockwork at a normal heart rate. Now, why do you have any QRS? That's the real question. It's because if your ventricles, and especially your sort of bundle of His and Purkinje fibers, if they're quiet long enough, they'll eventually have a pacemaker behavior and fire. But it'll be at a very slow rate. 1, 2, 3, 4, 5, 6, 7 boxes. That's going to be where you pick up. So if your if your AV node is completely blocked, you're not necessarily dead, but all of a sudden you've got this really slow heart rate for the ventricles because you're depending on not as the pacemaker. Your SA node's not the pacemaker anymore. It's somewhere in the AV node or down in the Purkinje fibers, bundle of His, becomes the pacemaker, and it just slows things down. So this person's probably fainted. This person's not dead, but this slow of a QRS complex, and your atria and ventricles are all out of sync. So you're not pumping the atrium and then pumping the ventricles like you want to fill the ventricles. So you're ineffective pumping of each beat, a really slow heart rate. People who have third-degree AV block, well, sometimes third-degree AV block comes and goes. Sometimes you'll have it intermittent, so that you'll be going along with a normal life, and then for some reasons, hard to say why, your third-degree block will kick in, and you'll have this, and you'll faint. So if you have that, well, you can't drive. You can't drive because if you were driving and you fainted, it'd be a disaster. So, some people even wear football helmets around because they fall over and faint and hit their head. So it's a serious problem. This was, in fact, the first disease treated using pacemakers, was to try to treat third-degree AV block. And pacemakers are great for it because then you can just pace the ventricles at the proper rate and you solve the problem. So we'll talk more about that next class. Third-degree AV block. We'll run out of time. So
yeah. This is where the P wave is like working, but the QRS complex is.
The P wave looks fairly normal. The QRS looks fairly normal, but they're completely out of whack. They're not dropping like every third beat like clockwork. They're just like two metronomes that are set to different frequencies, and they each beat on their own, completely uncoupled from one another. So you have to watch it a while to really appreciate that. But they're two properly running metronomes, but no coupling between the two of them. Okay.
Is there no T with that one?
Let's see. T's. This would be. Let's see. This would be the T. It's kind of delayed T, but you can see a T wave there, following that QRS. There's a T wave. This is the T wave with the P showing up between the QRS and the T, so it's kind of confusing. So yeah, it does look like there's kind of a delay between the QRS and T, and I'm not sure why. All right. Premature ventricular contractions. It looks like a fairly normal heart rate. We got small boxes, so it's hard to see, but you have P, QRS, T, kind of small. And then occasionally you get this big boom. And that is somewhere in your ventricle, there's some tissue that wasn't very healthy, and it fires on its own sort of randomly. And that makes the ventricles then fire. But the way it fires looks confusing because usually you start here on the inside of this surface fairly uniformly, and then it propagates across the heart wall. Here it starts at one spot, and then it's got to propagate all the way through the heart, and it takes a lot longer. And that's why you have this wide, kind of funny shaped QRS and T complex. And in this case, the T is inverted like you'd expect. So these are not. I mean, this is strange looking things. I remember when my mom was in the hospital once, and I'm sitting there in the intensive room. She's unconscious, so you just sit there and you watch the electrocardiogram. There's nothing else to do, and every couple minutes, one of these things would pop up. And if they pop up once every couple minutes, it's not that big of a deal. But if they start popping up all the time, it's worrisome. Now, it's not terribly worrisome with these appearing, and sometimes if a person has these, they'll feel them almost. They'll feel palpitations in their chest, like extra beats. These are often premature ventricular contractions that they're feeling. When it really gets risky is if one of these happens right during the previous T wave, and then we'll see in a later class how you get you get the wavefront interacting with the T wave, and you can get the reentry starting. So the real concern is this will lead to a more severe arrhythmia, like ventricular tachycardia. This looks a little bit like atrial flutter, except it's the ventricle that's doing the fluttering. So you have a big reentrant circuit going round and round in the ventricles. So the signal, you can't even see P waves hardly, or the P is almost invisible because the ventricle signal is overwhelming it. It almost looks like a sine wave. It's very oddly shaped. It's going very fast because it's not being driven by the sinus node. It's being driven by how long it takes to run around in this circle. Ventricular tachycardia, very dangerous. It looks like you ought to be pumping a lot of blood, but actually each pump is very ineffective. So you're not pumping a lot of blood. Tachy, fast heart rate, is a fast ventricular rate. Okay, so this person is probably not dead, but this person is in danger. This person you need to treat immediately. All right, now, the worst thing is fibrillation in the ventricles. So in the ventricles, you got wave fronts going around in all kinds of crazy, chaotic ways. So each spot in the ventricle is kind of not talking to the other. If they say that if you take sometimes you do experiments on animals like dogs. You take a dog heart, and if it's in ventricular fibrillation, it's just going to quiver in your hand. It's not pumping, but it's not silent. It's just quivering like that. Not really pumping blood. You're not pumping blood, you're not going to be alive long. So if your ventricles aren't pumping blood, you're going to be dead. You're going to be dead in 10 minutes. Going to ventricular fibrillation, you've got 10, 15 minutes before you're dead, because you're not getting blood to your brain, to your heart, and other important organs. So this is why you need defibrillators, to give the big shock, and we'll talk about those next class, to stop the ventricular fibrillation. Notice it's not a dead heart. It's not a heart that's completely shot, because it's got this noise. It's got electrical signals. It's just they're irregular and difficult and not contracting in a synchronous way. So ventricular fibrillation, fibrillation is why you need defibrillation. We're going to talk a lot more next class about that. Okay. And then finally, one last one, asystole. That's just the flat line. This is where you go after you've been in fibrillation for a while, and now your heart just basically dies and no longer has any electrical signals, and it's a flat line. Sometimes it can be a flat line because you're frozen, and then in the case there's a slim chance you can warm you up and restart it. But basically, this is dead after you've been dead a long time. So you don't want that. You don't want fibrillation. But at least with fibrillation, you know you got a shot if you have a defibrillator around. So those are your 12. Okay, so you guys can be the doctor now. So here are some of you probably interested in going to pre-med. So let's just say you're the doctor. And here you see this electrocardiogram. Okay. What's your diagnosis? Yeah.
Atrial tachycardia.
Atrial tachycardia. That's actually a pretty good diagnosis, but that's not technically the way we say it. Because if you look back at the atrial, there was two atrial problems, atrial fibrillation and atrial flutter. So which one do you think of those two would be?
Atrial flutter.
It'd be atrial flutter. But if you said atrial tachycardia, I'd be tempted to take it, because if you really understand what's happening, it's a fast P waves, boing, 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 but they're not normal, chaotic P waves. It's fast and occasional QRS. It's atrial flutter. So it's a problem of the atriums. Okay, good. What's wrong with this person? Yeah.
Looks like sinus bradycardia.
This is a sinus bradycardia, a really slow heartbeat. So this person comes in, and unless this person is, Michael Jordan or Usain Bolt or somebody, you're probably going to say, I think you need some of these pills to give you something that will kind of increase the heart rate. Remember, the SA node gets a lot of neural input, so you give them a pill that will tell the brain to start signaling to increase your heart rate. It's basically you want to initiate the fight or flight response. That's what it takes to get the heart rate up. So if you give pills that would sort of put you permanently into a fight or flight response, that could take a bradycardia and put it into the normal. But that's what it is, sinus bradycardia. Okay, what do you got here? What do you have?
Ventricular tachycardia.
ventricular tachycardia. It looks almost like a sine wave. We got some funny little blips on it, but it's basically when they see the signal this big, it's almost certainly in the ventricles. So it's ventricular something, and it's going at a really fast rate, and it's really odd shape. That's a ventricular tachycardia. So there you go. Alrighty. This one's a little bit tricky. What do you think this one is?
Ventricular fibrillation.
I would consider this ventricular fibrillation. However, it's sort of on the border between ventricular tachycardia and ventricular fibrillation. A pure tachycardia is one reentrant loop. And pure fibrillation, you got multiples. In this case, it looks like maybe you have 2 or 3 and they're kind of out of sync, so you kind of got a beat frequency thing going on. Most people would call that fibrillation, but it's a more organized fibrillation. So I guess the bottom line is these electrocardiograms, they aren't always, they can merge into each other. And this is a case where you have a somewhat organized ventricular fibrillation. One thing about a tachycardia that's really dangerous, ventricular tachycardia, is this can, if it's left to itself, fairly rapidly turn into this. And then you're in the case where you need the defibrillator, you're dead. Okay, do I have more? Here's another. This one's kind of difficult. What do you think? Not really a tachycardia, because there's 5 boxes, so it's actually closer to a bradycardia than a tachycardia. But there's something a little bit wrong with this. First degree AV block. That time between the P wave and the QRS is not quite as exaggerated as this last one we looked, but it looks just a little bit too long. So this person, you keep your eye on them. All right, now, one more thing here. This is your homework. It's not actually homework that you're going to be graded on, but there is this website. I'm going to send you this whole PowerPoint. I hope I'll be able to send it through Moodle. I think it will fit. If I can't, I'll just send you the link here. You go to this website, and it's a game. And you can click on play the game, and it'll start sending these electrocardiograms across. And notice we have 12 you need to know. Here you've got a lot more. So it's gonna be more than you need to know. But you can play this a game, or you can just click on the different ones that we talked about, and you can see what they look like. And it's kind of fun. It's kind of fun. So if you can get so you're pretty effective at all these, you'll know more than you need for this class. So I will not assign it as a true assignment. It's not going to be graded, but I would encourage you to play it, because I'll give you one hint. On the exam 3, if there are some electrocardiograms, they're probably going to be electrocardiograms that I took as a screenshot from this game, because that's the easiest way for me to get an electrocardiogram. They're nice, clean, they don't have a lot of noise, not a lot of DC drifted things, so it makes a nice electrocardiogram. So it'd be useful to kind of get to know what the electrocardiograms look from the game. So I'll leave it to you to play the game. And that is what I had about the electrocardiogram, unless anybody else have questions. Okay, in that case, you have a really good weekend, and I'll see you Monday, and we'll start talking about how you treat these problems with pacemakers and defibrillators.